Hello, this is another one in my series of videos reviewing a data set of underwater images that was collected for the purpose of making a 3D model of coral reef landscapes. If you haven't seen one of my videos like this before, the idea is that collecting good data is 90% or more of the challenge in making photogrammetric models of underwater sites. And although this is something that any skilled diver could do, there are some common pitfalls I see regularly, so I wanted to share examples of these obstacles as I see them, so that we all might learn something and hopefully save time and collect better data sets in the future.
Okay, this data set shows a fairly subtle problem, but important problem that's also related to data acquisition. It's a fairly small site of coral restoration, only about 6 by 8 meters or something like that. You can see there's excellent alignment with the cameras, 492 out of 492 images aligned. That's what we're shooting for, 100% alignment. That's really good. But that's not the problem here. The problem here is with the swimming pattern. If we put the cameras on, you can see that these images were acquired by swimming only in one direction across this site. Okay, I want to re-emphasize here that there's two reasons why we're supposed to swim in two directions across the site to get double coverage. One reason is to try to prevent holes in the data and also to reduce occlusions. We want to try to get data from as many angles of each object as possible. That's not the problem here. You can actually see that there's good coverage on the sides of these objects. There's no big holes in this image, so coverage isn't the issue here. But the other reason to swim in two directions is to strengthen the geometric integrity of the image alignment, and that's the problem here. So I'm going to illustrate this problem by using the scale bars that are in this image. Notice there's quite a few of them that make it very convenient to use here. I put markers on these scale bars using the Agisoft marker feature. I put 3 at the bottom, 1, 2, 3, 4, 5, 6, 3 in the middle, 7, 8, 9, 10, and 11, 12, and 3 up here at the other end, 13, 14, 15, 16, and 17, 18. They're each supposed to be 50 centimeters long. So if we run the project report for this data set, you can see, again, from this, that the swimming pattern was in one direction only. But actually, there were a lot of views for all the points. You can see over 9 views for almost every point in this scene. So this is what I mean. Coverage is not the problem for this data set. But if you scroll down to the scale bars section of this report, you can see that there is systematic bias as you move from one end of the site to the other. Scale bars 1, 2, 3, 4, 5, 6 were at one end. You can see they all have slightly positive errors. 13, 14, 15, 16, and 17, 18 were at the other end. They all have slightly negative errors. And the scale bars in the middle have values in between the ends at the extremes. So the point is that these scale bar errors are not randomly distributed across the scene. They're positive biased at one end and negative biased at the other. This is a manifestation of the bending effect that I talked about in an earlier lecture with the Legos, okay? There's systematic geometric distortion across this scene because the images were acquired in only one direction. There were no tie lines.
So in conclusion, this example falls into the not enough tie lines category. We have good images, a nice swimming speed and height off the bottom, but the images were collected only in one set of parallel passes with no perpendicular tie lines. I'd like to acknowledge support for this series of videos from the Pew Fellows Program in Marine Conservation at the Pew Charitable Trust. And that's it for now. I hope this helps you collect better data for your projects.